Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on control systems, and this being probably the third lecture in continuation with the earlier two lectures where we shall be dealing with state space. As I said, the rest of this course we are going to completely dedicate ourselves to the study of the state space methods for control systems, which are commonly termed as part of modern control. So let me quickly take off from where we ended in the previous day. The last lecture we were actually talking about the so called phase variable form, and until we ran out of time, so when I said that we'll talk about this more in detail in the next lecture. Where are we currently? At this moment, this is what we can do, this is what we have learned about states. Quickly to summarize this, we have seen that if you are given an ordinary differential equation, of course you are very familiar with the transfer function mode of dealing with things. But we saw that there are certain lacunae or drawbacks, such as the lack of internal description in the transfer function domain, which motivates us towards the state space method. And then we saw that given any differential equation or its corresponding transfer function, there is a way to draw this so called block diagram, draw these bank of integrators and take the output of the integrators as states and get our differential equations in terms of, or the nth degree differential equation in terms of n first order or first degree differential equations. Yeah, we saw that. Then we saw that if you have more insight about a system, you might sometimes make a more judicious choice of states, not necessarily confined to this this analog computer realization version of it. Like in the RLC circuit, we saw that a judicious choice could have been the current and the voltage. In fact, you could have also chosen, if you are like someone from electromagnetics, you might also choose like the flux, yeah, the magnetic flux. So you know, L di dt, Li is basically the flux, right? So that could also have been a choice of states. Anyway, that aside, that cannot be a very concrete method because that is specific to the system, right, and your understanding of the system more specifically. But the other method is this phase variable method, which promises us this liberation from having to draw this block diagram every time you encounter a differential equation. Yeah, so this is more like an algebraic method rather than a schematic way of drawing this state variable representation. So let's see where we were last day. So we took the same differential equation for which we drew that that block diagram and then derived the state space equations. So we'll take that same equation here, yeah, and we saw that let us keep on defining the states like so. So define x1 to be the output, y. That is what is appearing in this differential equation. The x1 dot is equal to y dot is equal to x2, so on. So because there are only 3 differentiations that happen to y, it's a third degree differential equation. So we only go as far as x1 triple dot. But as soon as we get into x1 triple dot, it seems like there is a problem, yeah, and this is why I stopped, because this requires some explanation. So at this point, just hang on. What is this problem? The problem is I have only one input, which is u, yeah, but here on the right hand side it seems like the derivatives of the input also appear. Now this is unlike anything we have seen, right? We have seen that our description of the system is x dot is equal to ax plus bu, yeah, this is what we described in the previous day, right? This. Now nowhere in this picture do we see any u dot or u double dot or anything of that sort appearing, right? So it seems like we have run into trouble now, right? Where do we go now from here? How do we account for these u double dot and u dot and u? And this is where this beautiful property of linear systems, this so called superposition, saves the day for us. How so, you might ask? So bear with me a little and all will be explained, all will be revealed. Okay, so here is how it goes. For the moment you imagine as if these higher derivatives of u do not exist, yeah, imagine that these higher derivatives of u do not exist. So there are two things that happen here. First, superposition due to linearity, yeah, because we are dealing with linear systems, because it's a linear ordinary differential equation, so it will have this property of superposition. Remember many lectures back, right at the beginning, maybe 6th or 7th lecture, I don't recall, right, we discussed this linearity of the response of a differential equation. We actually showed that for a general nth degree differential equation, if I recall. Now we are convinced that this is linear in the sense that if you have an input u1 and an output corresponding to it as y1 and an input u2, output corresponding to which is y2, then the output corresponding to alpha u1 plus beta u2 is alpha y1 plus beta y2. So schematically we have u1 leading to y1, just to refresh your memory, this is something that you are already familiar with, u2 leading to y2, then you have alpha u1 plus beta u2 applied to the same system gives you alpha y1 plus beta y2. So this is basically linearity, yeah. So this superposition principle works in a linear system. The second observation is, this is the first key observation, the second observation is the highest derivative of u is less than or equal to the highest degree, let us say the highest degree derivative of u is less than or equal to the highest degree derivative of y. Why is this so? Because remember we are always going to deal with at most strictly proper systems, we do not deal with improper systems, yeah, we have already said that so many times in the light of transfer functions, and that is the reason why when we had 3 derivatives here I chose 2 here, I could have gone for 3 up to 3, and in that case also you would see that this description would be inadequate, we would have to add some term like du, but again I will withhold that explanation for later, maybe in this lecture itself I will explain that, but not now. For now I am going to tell you that even though it appears like handling this u dot and u double dot is like an insurmountable challenge in this so called phase variable form, we will show you that because of this superposition and the fact that the highest degree derivative of u is less than or equal to the highest degree derivative of y, we will still be able to describe this system, yeah, in the phase variable form, and that phase variable form will be very interesting and very revealing, okay. So hereafter once you have learned this phase variable form, you will see that having to draw all this circuit diagram or this block diagram is going to be completely redundant. You at least have one form which you can write immediately just by looking at the differential equation, okay. Lots of promises, yeah. So what is this phase variable form? Should get you excited about it now, right, okay. So first consider the system y triple dot plus a1 y double dot plus a2 y dot plus a3 y is equal to b3u, is equal to b3u, right, okay, great, right. Now this we can easily handle. Now consider this earlier description, so these terms would then vanish. So in this case you would have, let me just write the last line here, repeat the last line here, sans this u double dot and u dot, because now we are only considering this b3u to exist and these two to disappear. So we are going to consider this last equation now. So x1 triple dot, this is the stage where we ran into trouble, right, with this u double dot and u dot, but now if we say that b1 is equal to 0 and b2 is equal to 0, so then these two fellows do not exist, yeah, so that is the easy case. So then I have this x1 triple dot is equal to minus a1 y double dot minus a2 y dot minus a3 y plus b3 u. But recall, what is y double dot? Y double dot is x3, yeah. So I am just going to replace this with x3. What is y dot? Y dot is x2. So I am going to replace this with x2. What is y? Of course, that is x1. So this then gives me minus a1 x3 minus a2 x2 minus a3 x1 plus b3 u, yeah. So then for this system where b2, where suppose these nasty derivatives, yeah, for now let us assume that phase variable is incapable of handling these derivatives, yeah. So we are only giving the phase variable method what it can handle. So apparently now that I have removed this, now that I have assumed that b1 and b2 are 0, this b1 and b2 are 0, these nasty fellows are 0, I am only dealing with this b3. So I should be able to do this, because now clearly what does this first line tell me? X1 dot is equal to x2. So the complete description is, this is x3 dot, x1 triple dot is what? X1 triple dot is basically x3 dot, yeah. So this is x3 dot, and x2 dot I already know from before, x2 dot is equal to x3. See, I have to represent everything in terms of x1, x2, x3, yeah. I cannot afford to have derivatives on both sides of this equation, yeah. That is the idea. I want to have all first degree differential equations. So nth degree differential equations split up into n first degree differential equations. That is what the state space description is, that is the state space form is. And x1 dot is equal to x2 dot is equal to x3, and x1 dot is equal to x2. So x2 dot is equal to x3, as you can see here. It is this part that I am focusing on. This, yeah, this x3 dot is equal to this, and x1 dot is equal to x2. So now if I write this in the compact form, notice what it's going to look like: x1 dot, x2 dot, x3 dot, yeah. x1 dot is equal to what? It's going to be x1, x2, x3. So this is going to be 0, 1, 0. x2 dot is going to be what? x3, that is 0, 0, 1, 0 times x1 plus 0 times x2 plus 1 times x1, x3. What about x3 dot? x3 dot is going to be minus a3 times x1 minus a2 times x2 and minus a1 times x3, plus what about b3? b3 is going to be 0, 0, b3, sorry, this is the B matrix, times u, yeah, because the input does not appear in the other equations, right? x1 dot and x2 dots expressions do not contain u. Now notice the beautiful thing about this, yeah, how are these a2, a1 and a3 related to the original differential equation? They are just the coefficients here. So the moment I look at a differential equation like this, the phase variable form is apparent immediately, yeah. So instead of now writing this b3 here, here's what I am going to do, okay. I am going to say that this b3 is, suppose 1 here, yeah. So that will actually help. Hang on, if you think that I am just doing this ad hoc, which probably I am, but there is a reason. So I am just going to sort of take this as 1, yeah. I mean, if its b3 is non-zero, I can just scale it down. It's, as I said, we saw in the superposition principle here, we understand what the response due to u is, we understand what the response due to alpha u is, yeah. So I can just make it like 1 times u, yeah. Now what about, so this is basically the response, so y is going to be given by what? Y is basically nothing but x1, so it's 1, 0, 0 times x1, x2, x3, alright. Now let me call this y response due to u, okay. So then what is the response due to B3u? Well, of course, it is the superposition principle that comes to my rescue. See, in this ordinary differential equation, the input is, in this original ordinary differential equation, the input is u, the output is y. But now I am trying to take piece by piece, and the hope is that if I understand what the response due to u is, I should be then able to understand what the response due to B3 times u is, and by extension, and this is the beautiful thing, I should be also able to tell you what the response due to u dot is. Look, if the response of a system due to u is y, then what do you think the response of the system due to, it is a linear system after all, what is the response of the system due to u dot going to be? It is going to be y dot, right? That is it. That is the essence, that is what allows us to represent things in this phase variable form, yeah. So this is going to be, answer is going to be B3 times y. So now if I plug this back in here, if I plug this back in here, this B3 and this B3, you see I do not need to touch this x dot is equal to ax plus bu form. All that I need to now do is replace this with B3, that is it, no, I am done. See, get the idea. If I did not have B3, if I had just unity as the coefficient of u, the response would have been y. Now I am just multiplying the input by B3, so my output side, the output better be also multiplied by B3, yeah. And then superposition does not only say that I can scale it up, I can also add scaled versions of inputs to themselves, right. So now the next question, what is the response due to u dot? The answer stares me in the face. If the response due to u is y, then the response due to u dot is going to be y dot. Why? Simple. What am I basically saying? I am saying that this is my system, this is my LTI system, I am giving it an input u and it is spitting out y. Now I am saying that I have this input passing through a differentiator, yeah, and this is an LTI, this is the LTI system in question. So what do you think it is going to be? I can play around with this, so I can push this out, yeah, they commute, no, that is what we saw. You see this LTI system, it allows us to have this commutation of these operators, right. So then we can put this here, this LTI, this is actually tantamount, these are equivalent systems, right, these are equivalent systems. I can put this differentiator at the output end and have this u here. So what is this? This was my erstwhile y, so now this is my y dot. So basically then this is u dot being applied here and this will spit out at the output terminal. So if this is my entire black box here, whether I put the LTI before the differentiator or after, it does not matter. So now I know that the output is going to be y dot. So if I now replace this with B2 u dot, then this will be just B2 y dot. Similarly, I can keep going around and doing this differentiation operation. Of course, I am not saying that the actual system contains a differentiator, this is just for representational purposes, okay. So this is just for representation, okay. Do not go ahead and assume that the actual system also contains a differentiator like this, okay, that will be incorrect, yeah, the actual system does not contain a differentiator like this. This is just what I am doing to convince you that it is nothing but superposition principle at work, yeah, okay. So now having seen this, we know that this is going to be B2 times y dot. Similarly, what is the response due to, let us say, B1 u double dot? Of course, the answer is going to be B1 y double dot. But what is y dot? This is going to be B2, recall that y dot, the way I have defined the phase variable method, the y dot is nothing but x2. So this is going to be x2. What is this y double dot? this is going to be B1 x3. So then you see, once I have actually, and this is the beauty of it, initially you might have been a little fastidious and might have been thinking that I am simplifying the problem too much, right. I am just taking as if this only this part, this B1, and making the taking this B3 and making this B1 and B2 0 is a very drastic assumption to make. It is actually not an assumption. I am just showing you, I am just convincing you that you just can take this B3 part alone, study the effect of this u alone on this differential equation as the forcing function, and then if you know the response of this, response due to this u, you also know the response due to u dot and u double dot and all its higher derivatives. Yeah. Only problem is if you now considered u 4 dots, you have a third degree differential equation in u and you consider a 4th dot, which would basically entail an improper transfer function, then again you will run into trouble. Yeah, but as long as you go up to the 3rd dot, even if you had a B0 u triple dot, we will come to that shortly. Yeah. So then what we do is we keep this x dot part unchanged. It's going to be 0 1 0 0 0 1, as you can see here. Yeah, this same representation is going to be unchanged. Yeah, it's going to be minus a3 minus a2 minus a1 x plus 0 0 1 times u. The only change that is going to come about because of these terms being present is, notice that you are going to have b2 times x2, b1 times x3 and b3 times, this is nothing but b3 x1. So earlier when you had just this one acting, you had these two entries as 0, but now they will also have non-zero entries. So you will have this b3, b2, b1, and the reason why we think that this phase variable form is beautiful is precisely this. You see, in these A matrices, A, B and C matrices, yeah, the variables, that the numbers that appear are directly picked from this differential equation. Yeah, they just happen to be the coefficients of this differential equation, either the coefficients of the input or the coefficients of the output, nothing else, right. So all that idea about having to draw that block diagram, then call that output of the op amp, that might have some physical significance, that might tell you something about the so-called memory of the system that is being conveyed or carried forward by this state, right. Everything that has happened to this system up until the instant t0 is carried as if embedded within those initial conditions, right. So that is why that has a physical significance. But if you are really someone who is into deriving a state space representation of a differential equation quickly, yeah, then it seems that this is the most convenient one of all after all, right. Whether I give you the differential equation or the states or the transfer function description, you see these are nothing but the coefficients of s, s squared, s cubed, yeah, and the constant in that transfer function, right. That is all that you are dealing with in representing it like this, right. So therefore this phase variable form is a particular favorite in some sense. So people are a little biased towards this phase variable form. Later on, as we go further into this, we will learn that this phase variable form also has something, some beautiful feature in so far as this property of controllability is concerned. But again, all in good time, let us not get ahead of ourselves, right. So now where are we currently? Again, to take stock of the situation, we have seen that there are these states that allow us to have internal descriptions. We have seen that given a transfer function or an ODE, how to get this state space representation by drawing either the block diagram or by doing a bit of algebra with these so-called phase variable form of the state space representation. So now, given any transfer function or ODE, you should be quickly able to derive at least one state space representation. But the question about whether they are unique is now rendered like meaningless. We have seen that there are multiple representations. However, the question that still remains is there any connection between these state space methods? So to summarize all of this in a sort of a pictorial form, here is what we have seen thus far. So suppose you have an ODE or a transfer function, yeah, like this given to you, then it turns out that I can have a state space realization 1, I can have a state space realization 2, right, like this. I can have another state space realization 3. So for example, one of your friends suppose is more into algebra, that person will probably prefer the phase variable method, and the other friend is more into drawing stuff and these circuit diagrams and wiring diagrams and all, and that friend will probably adopt the first method that I have shown. Yeah. So he or she might be actually drawing those op amps or these integrators and calling the outputs of those integrators as the states and getting a corresponding ABC matrices, right. Yeah. So of course this is not unique. Yeah. So given an ODE, yeah, we have seen that there can be several representations. In fact, we have not yet shown this, but I am claiming, and maybe later on we will have time to sort of convince you about this, there are infinitely many state space realizations for a given ODE or a transfer function, and we have seen how to get from this ODE to this state space realization. One question, sort of a question that might be bugging you a bit at this point, yeah, I mean I have not answered this, and this you will see that it might appear even in the earlier form as well, like the one we discussed earlier, this particular form. Yeah. So what if your ODE that you started with, yeah, what if there was a term, say something like, okay, how do I write this? Let me use a different color. So what if there was a term like, say, B naught U triple dot? Yeah. So what if the degree of the derivative of U and the degree of the derivative of Y, what if they match? I mean that is a strictly proper transfer function, right. You can easily read that this would give you a transfer function like B0 S cubed plus B1 S squared plus B2 S plus B3 upon S cubed plus A1 S squared plus A2 S plus A3. Yeah. So you can have a transfer function like this after all, right. Notice all we have said is that it cannot be improper, but a transfer function can be biproper. Now you might wonder, in that case, can we still represent a state space system in the form that we have discussed so far, that is, can we still have a state space description of the system given by this x dot is equal to Ax plus Bu and y is equal to Cx? Is it possible to represent a biproper system in this form? Yeah, this question might be bugging you a bit, and rightly so, it should bug you. Yeah. So of course we say that, as I have hinted in the earlier lecture also, what we then do is we add this so called feed forward term du, and how does this help, you might wonder. Well, let me explain in the context of both those realizations how this helps. So now look at the phase variable method. Yeah. So suppose now here you also had that say B naught Y triple dot. Yeah. So if you had B naught Y triple dot, what would this representation have been like? Yeah, because Y triple dot is nothing but, yeah, this x3 dot, Y triple dot is something that is already appearing in this left hand side of this equation, no? Yeah. Where was that? Just a minute. Yeah, yeah. Here you see this Y triple dot is something that is already appearing here on the left hand side of this equation. In fact, by putting this Y triple dot on the left hand side, we put everything back on the right hand side, and that is when we studied this, right. So then you might wonder, what is going to happen? How are we going to handle this term? Yeah. So and at an even earlier stage, you see when you had this this block diagram realization, of course here I would put it to you that it is actually easier to see. So notice what we did here. Yeah, What if you had a, in fact let us just see this first. Suppose you had a B naught U triple dot, yeah, B naught U triple dot was suppose on this side as well, right. So then you would have had a BU, B naught U, right, because that triple dot would have been just like this, Y would have been freed up of this triple dot, this B naught, this U would have also been freed up of this, right. So none of this would have passed through this integrator. So here what you would have then done is, and that is why it is called a feed forward, you see, you would have passed this B naught without letting it pass through any integrator, you would have passed this through just a B naught gain and would have summed this here before calling it the output, yeah. So you would have summed this here, that is what you would have done, you would have had a summer here instead, yeah. So that is why this term du, as I said here, this term du, this is often called a feed forward term, because it is as if being fed forward without, it is like bypassing the entire system, yeah, it is bypassing this entire system, you see, it is ignoring all these integrators. Why? Because it appears directly as it is. You see, if you had this plus B naught U triple dot, the moment you pass you hit this with 3 integral actions, so integrating thrice with respect to time, this U triple dot would just spit out this U, so you would have had just this B0 U, yeah, and this B0 U means that in this block diagram here, this U without passing through any integrator, just pure form of U just passes and gets added with whatever comes through all that integrator action, it just gets added with it and just passes through, so it is a feed forward, yeah. So if you have a strictly proper transfer function, then this x dot is equal to ax plus bu and y is equal to cx is inadequate to capture that, then you also need this so called feed forward term, but again this is a corner case, in most cases you will be dealing with strictly proper transfer functions rather than by proper ones, so at least you are sure that you will not encounter this d, yeah, but anyway it is good to know. But now in this phase variable form also, let me convince you where the difference will be. What I am going to say is that, you know, this B naught is just going to appear as minus B naught here, minus B naught here, I mean B3 minus B naught here, B2 minus B naught here and B1 minus B naught here, and with a plus B naught U here, yeah. So this is going to be the D matrix. So in general for a seesaw system, you see, what is the dimension of this D matrix going to be, the size of this D matrix, D is going to be just a real number, because the output is 1, the input is 1, so it is just a scalar, this D is going to be a scalar, so this fits. So why is this going to be B3 minus B naught, B2 minus B naught and B1 minus B naught, and this is going to be just this B naught here, yeah, just think about it, yeah, what is happening. See, again the beautiful thing about the phase variable thing is that this x dot is equal to ax plus bu, the a and b do not get affected by this, yeah. So you might wonder why this is happening. Of course this you might immediately guess from the circuit diagram or the block diagram we had drawn earlier, but still in view of this, because this phase variable form is just an algebraic approach, right, so we should be able to see it algebraically why it is happening. So what is this B naught y triple dot after all, yeah. So what we need after all from this B naught y triple dot is, if we know y, then y is equal to, y without this B naught is going to be this, sorry, B3, B2, B1, yeah, let me go to that. So the y due to the, so it is going to be B3, B2, B1, yeah, this is the y in the absence of this B naught. And now if you take this y, yeah, and if you take its third derivative, what is its third derivative going to yield after all? Its third derivative is going to yield nothing but this, yeah, this, sorry, where was I, yeah, I am just getting confused here with this slide numbers. So this is this y bar, sorry, this y bar is, I should write in black, so it is this y bar here, is the output when B naught is equal to 0. So this it is a strictly proper transfer function, and we know this y bar what it looks like this. Again, please do not get confused with the notation. Earlier I called this y, but now I want to call the y the net effect due to this B naught y triple dot as well, so I am just calling this y bar. So this is going to be nothing but equal to B3 B2 B1 times x. Yeah. So then now notice, yeah, so now here we studied the effect of due to u, then we said that if you know the effect due to u, you know the effect due to u dot, u double dot, u dot, so on, and then the effect due to u triple dot is going to be nothing but this, but what is this? This is going to be nothing but B naught, and you write the expression for y triple dot, yeah. And if you write the expression for y triple dot, what is y triple dot's expression? Y triple dot's expression is captured in this third row here, right, plus this u. Now what about this third row? Now you cannot keep this x1, x2, x3 free as it is, right, yeah. So those will be, I guess, reflected with B naught times. So I think I missed a bit of a trick here. Probably what I missed here is this B naught times, this will be A3, this will be A2, this will be A1, yeah. So this will be B3 minus B naught A3, B2 minus B naught A2, and B1 minus B naught A1, yeah. So notice that if this B naught is 0, then it collapses back to the original response, right. Why am I saying this? Because of course this y3 triple dot is captured by this row times this x plus u, so that is y3 triple dot. Now B0 times y3 triple dot is nothing but B0 A3 minus B0 A3 x1 minus B0 A2 x2 minus B0 A1 x1 x3, sorry, what did I say? So let me write that down, minus B0 A3 times x1 minus B0 A2 times x2 minus B0 A1 times x3 plus B0 u, that is equal to B0 y triple dot, yeah. So that is going to be added to this. So if that is going to be added to this, then B0 u is already appearing here. But what about these terms? See, already they had this B3 times x1, B2 times x2, B1 times x3. To that you now subtract this. So therefore you have B3 minus B naught A3, B2 minus B naught A2, B1 minus B naught A1. That's it. So that's the modification. So whether you do it algebraically or you do it using that block diagram, this is how it is. But in general you will not encounter this sort of a bi-proper transfer function. You will mostly have strictly proper transfer function, in which case you just put in this B naught 0 here, and you see that it collapses back to this B3, B2, B1, this beautiful form. So in other words, we have convinced you that there are at least two very clear-cut, easy ways to represent a transfer function or an ODE in the state space form. Now the next question is, can we go back the other reverse direction as well, yeah. So given a state space realization, can we go back and get an ODE or a transfer function back from it? Can we recover this, excuse me, can we recover this ODE, yeah. So that is the question that we shall concern ourselves with now, and once we have seen that, that will be the last thing we will see in this lecture, right. Okay, so hopefully we have now convinced you about this utility of this feed forward term when you have this strictly proper transfer function. We have shown it in both lights, yeah, in the light of the wiring diagram using op amps, and also in view of this phase variable canonical form, right, this phase variable representation. So now we ask ourselves the question as to whether we can go back, and in fact we have probably already done this at some level, but let us still try to push for this result here. So suppose you have x dot is equal to ax plus bu and y is equal to cx plus du. By the way, So I am just considering the possibility that it is probably going to be a biproper system, right. So that is why I am including this D here, yeah, but in most cases, as I said, you will not have this D. So by the way, in MATLAB there is this command SS to TF and TF to SS, right. So you should try them out, you should read their syntax and try them out. So if you feed a system, if you describe a system in terms of state space and you want to see its transfer function, then you have to use the SS to TF command, see what its arguments are. So this could be a nice exercise for you. And if you are given a transfer function described in terms of the numerator and denominator polynomial, so you should learn how to do that in MATLAB. Then if you want to find its state space description, of course it is not unique, so MATLAB will just have, depending on what algorithm it uses, it will spit out one of those non-unique, one of the several possible state space representations, right. So you should also look that up, yeah, give some numerical values and figure that out for yourself. It is an interesting exercise. Yeah, so now let us get to the final point of this lecture, how to get from the state space to the transfer function. We already seen how to get from transfer function to state space. So here is what we are going to do. Take Laplace transform of both equations, right. So here you have, for example, x1 dot, x2 dot, x3 dot, like this till xn dot. If you take the Laplace transform of this, what will happen to this? This will become s x1 s, s x2 s, likewise you will have s xn s, yeah. What will happen to this matrix and x? Yeah, the matrix is just a constant, right. So if you take Ax is equal to A times x1, x2 dot 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 till xn, if you take this Laplace transform, the A will remain unchanged as it is, it is just that these variables will look bigger, yeah, yeah, this is what it looks like. So as with all transfer functions, we assume, because if you want to get the transfer function, it is assumed implicitly that 0 initial conditions, right. So then where do we go from here? So we have this s x1, s x2, so these are all the transformed variables till s xn s, yeah, is equal to this A matrix times x1s, x2s dot 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 till xns, plus again this B matrix. So this is the A matrix, this is the B matrix, and the input gets also transformed, right, it is a scalar. So this is just a Laplace transform of this, yeah. What about the output? The output also we can take the Laplace transform. This is going to be, again, the C matrix does not change, so this is the C matrix, this is again going to be x1s dot 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 till xns, plus this D is going to be a scalar times us. So what is this matrix? What can we write this as? Notice that this is nothing but S, 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 like this sort of a matrix times x1s, x2s dot 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 till xns, yeah. This matrix is what I am talking about. So this can be further written as S, I can pull out this S, I can pull out this S outside, and this is just the identity matrix. It is just the identity matrix, no? Yeah. So by that same token, then what we write this as is, we have Si xs is equal to A xs plus B us. So therefore, let me bring all xs related terms on one side, because I want to eliminate x after all. I want to get the relation between y and u. That is the goal of a transfer function. Yeah. So this x served as like some intermediate variable which I have introduced for this state space domain. So when I am now again intending to go back to the transfer function domain, I better collapse on these x's, yeah, get rid of them. They are of no use to me if I am going for the transfer function description, right. So let me try and do that. So this is going to be Si minus A xs is equal to B us. So obviously if I want to now write this xs, I have to hit it with Si minus A inverse on the left, yeah, and this Si minus A cannot be singular for all values of S, right. Later on we will see more direct implications of this, or more direct ways of seeing this, why it should be invertible, yeah, but for now you have to believe me that this is invertible, because after all this S can change, S is a complex variable. So if this is in, like, it cannot be that this S, no matter what value of S you take, this is going to be like singular, right. So we do not take this to be singular, and if it is not singular then it is invertible. So if it is invertible, then we have this BUS, yeah, so that is our x. And now plugging this into Ys is equal to Cxs plus Dus, we get Ys is equal to C times Si minus A inverse B us plus D us, which is nothing but C into Si minus A inverse B plus D times us. So therefore this Gs, or this transfer function that we talk about, yeah, the transfer function is going to be nothing but, of course, because it is scalar, we can divide Ys by Us, we can divide Ys by Us, and we can get this transfer function as C times Si minus A inverse B plus D, yeah, no ambiguity here. So you give me an ABCD matrix, and quite rightly therefore, you see MATLAB will also ask you to feed in, when you want to get from SS to TF, MATLAB will actually ask you to feed in the ABCD matrices, yeah. If you feed in the ABCD matrices, MATLAB will spit out the transfer function corresponding to it, and this can be uniquely determined. Given that the ABCD matrix is given to you, this can be uniquely determined. The reverse is not true. So if I give you some transfer function and I ask you to get a state space realization of the same, yeah, it is definitely not unique. We have seen at least two different ways of representing that, okay. So hopefully with that now we have seen how to go back and forth between a transfer function and state space realization. We have also seen how to, there is this phase variable method, which is an easy to read method from the ODE directly to convert it into a state space form. So an nth degree differential equation converted to n first degree differential equations, yeah, we have seen that very conveniently. We have also seen how to draw these wiring diagrams, these op amps, these integrator banks, and represent states as outputs of these integrators, but we have also seen that we need not confine ourselves to only those particular choices of states, right. So as we go forward with this, we shall see a number of more interesting results now. One of the things is, now that we have seen that there is a way to go about from transfer function to state space and state space to transfer function, we wondered if the state space method is actually self-sufficient in itself. By that I mean, like, look, if you are given a transfer function and if you are given the input, you know that you do not need to actually carry out the convolution in the time domain. You can actually take the product of the Laplace transform of the input and the transfer function of the system, and then take its inverse Laplace transform of that product, right. That gives us a very good handle on how to solve, at least for the particular solution of this differential equation. So now we wonder that having represented an nth degree differential equation as n first degree differential equations, yeah, can we do the same? Can we, by doing the same I mean, can we also solve for this differential equation, right? Is there a way to solve for this differential equation without having to go into this this so called transfer function domain, right? We want to independently be able to solve for this differential equation. So before we get into that, let me summarize in a figure what we have now seen here, right. So if I want to draw this schematic diagram here, this here is what we have seen. Here is going to be your bank of integrators here, yeah. The outputs of those integrators are going to be these states here, yeah, and here is going to be like your A matrix. So do not read this as a typical block diagram like the ones we have drawn earlier, but this is just a representation, and you will see how it makes sense, this transfer function, right. So this is a summer here. So this is basically an n channel, okay. So I am going to draw this as n channels in double lines like this, yeah, and then we have this C. Now it becomes a single line. So of course this is also a double line here, yeah. So this is n variables. So whenever I am drawing this double line, it means that it is not a single signal that is passing through, there are n signals that are passing through here, yeah, okay. And then you see you have initially a single input u being applied here, so this is a single signal. Then you have this b, so b kind of like vectorizes or transforms the scalar into a vector. So you have u, and then you have that transformed into bu. So u was basically a scalar, and bu now becomes a vector. So therefore it is from this side that this vectorization kind of starts, yeah. So what you have is this plus, so they kind of add here, and again the C de-vectorizes in some sense, right. So you have this x which is mapped to this Cx. So remember that this x was basically r to the n, and the Cx is now a scalar. So this is like de-vectorization in some sense, okay, if you permit me to abuse that term. So this is y. And in addition, in some cases you might have, so again I am dealing with seesaw here, so this is the seesaw representation, seesaw's representation. Of course just a schematic, so this is not going to be of any practical use to you, as in given a transfer function how are you going to write this down, no, that is not why I am drawing this, okay. This is just a schematic, and you will see that if you follow this schematic then you will be able to get exactly the state space equation. So in that case of course you will have to have a summer here that is added. So let me remove this y from here, because in that case you will have this y here, okay. So this is basically it, yeah. So this integrator bank has these initial conditions, yeah, which could be non-zero, yeah. So each of those integrators can have, for example, one initial condition captured by it, and that is how you can now solve for this. So what you do is you set some initial condition here, apply some input signal here. So you have a signal generator, for example, here, let us say, and you have an oscilloscope here, yeah, and you observe the output. So this is how you set up the solution of a differential equation. Once you have got this differential equation, and from there you have extracted what the ABCD matrices would be like, this is the schematic, this is the sort of wiring diagram if you like, if you want to implement, yeah, this is how you go about doing that stuff, okay. So that you should try to sort of wrap your head around and see that indeed this is capturing the system which we have described by x dot is equal to ax plus bu and y is equal to cx plus du. So in the next lecture what we shall see is that it is alright, we have got this representation, although we are still a little worried about, you know, whether, see, we have established the connection that from the ODE we can go to any of these state space representations, and from any of these state space representations we can go back to the unique ODE or transfer function from which the state space realization emanated. But it seems that the connections between these, if they at all exist, yeah, is not very clear to us, and this is actually not a very trivial or easy question to answer, you know. If you want to really study this in great detail, then you have to go into details of courses like multivariable control. We will try to give you a flavor for that, for when these relations exist. You will get at least some cases where these relations exist, yeah, but whether in all cases these relations exist, right, at the peer level. So it is like, you see, you have this ODE at this level, yeah. From this ODE you have gotten to many of these state space realizations, okay. Now each of these state space realizations, yeah, can we go from one state space realization to the other, yeah, and can we do that for any arbitrary state space realization? It will turn out that that will be contingent upon certain properties of the system, okay, yeah, and that realization. So many of these properties that we learn when we are dealing with state space, for example, controllability, observability, so on and so forth, you will see that these are not really per se properties of the transfer function. So from a transfer function there is no way you can talk about these things. It is only when you get into the state space domain that these things make sense. These are totally dependent on the way you are realizing the state space system. Again, perhaps I am getting a little ahead of myself here at this point, but nonetheless we will visit these topics in the coming lectures. But before that, maybe we will take up another example, maybe not of an electrical nature, because so far we only talked about these electrical systems. We will take a mechanical system because we have studied them in some detail. We have some idea about how to model those mechanical systems, maybe a translational mechanical system, yeah. So we will study that in the next lecture, and then we will concern ourselves with this question of how to obtain a solution, yeah, how to obtain a solution for this state space system, and whether independent of the transfer function domain, independent of this Laplace transform business, we can actually go about finding a solution for this state space system, yeah. We will study that. We will at least try to study one or two methods, independent methods, to evaluate or to solve for this state space system, okay. But all that will form part of our next lecture. So until then, please in the meantime try to practice getting from a transfer function to a state space realization. Try practicing both of these methods. Again, if time permits, before the course is done, we will show you different, at least a few more ways of realizing from a transfer function to a state space realization, yeah. We will show you a few more methods, and those representations, just like this is called phase variable, the one we have studied today, yeah, those representations also have certain names, yeah, and those names will only be obvious when we have understood terms like observability and controllability. So that is why I do not want to introduce too many representations at this stage. Only after we have understood those terms, those representations will make sense, okay. So we will get there, but maybe one realization we can cover before that is probably the diagonal realization. I will probably do that in the next lecture as soon as we have just talked about this solving. So maybe in the next lecture the two things we shall cover is, one, we shall see how to solve for this state space system of equations, these n first degree differential equations using Laplace transform and also without using Laplace transform, and then we shall see another method just as an addendum of realizing this state space form from a given transfer function, but in a different form. Hitherto we have only considered this bank of integrators in the cascade form. We shall see that we can also put them in parallel form and still obtain this state space realization. Of course, the A matrix will have certain special structures and properties, okay. So we will see all of that in the next lecture. Till then, take care.